Hi, I'm Jason Moore. I'm director of the Institute for Biomedical Informatics at the University of Pennsylvania. Today, I'm going to tell you about a project we've been working on for several years to provide accessible artificial intelligence for automating data science. So, a little bit of background. First of all, I think of health very much as a complex adaptive system. That is, there are many components. Think of these as genes, environmental factors, metabolites, proteins, etc. These components interact with each other in time and space to produce what are called control structures. Think of these as biochemical pathways, for example. Multiple biochemical pathways interact with each other to produce a system, and it's the output of the system that ultimately determines our health. Now, the feature of a complex system is that it's difficult to predict the behavior of the system or the output of the system from the individual components. To do a good job of prediction, you need to be able to understand how all of the components interact. Now, we live in a big data world. We can measure lots of information about humans. And putting big data together in the context of a complex system makes this a very challenging problem. And this is why we need artificial intelligence. So, for those of you not familiar with AI, let me just give a brief history. Artificial intelligence is the idea that we get computers to plan, solve problems, and reason. And in the 1950s, Alan Turing, the great computer scientist, asked the question, can machines think? And how would you know if a machine could think? Imagine getting out of bed in the morning, turning on your computer, having a conversation with your best friend, speaking with them later that day and saying, hey, that was a great conversation we had this morning. Your friend says, oh, that wasn't me you were talking to. I was still sleeping. You were talking to my computer. At that point in which you can't tell the difference, whether you're between a real computer or a real person, the computer is said to pass the Turing test. Now, it's exciting because we are now in a period of time where there are legitimate claims of computers passing the Turing test. This was one of the first claims. This is a computer chatbot called Eugene Guzman, which simulates a 13-year-old Ukrainian boy. Now, someone put this to the test and asked 30 humans to use the chatbot and answer the question of whether they were talking to a real person or a computer. And 10 out of 30 people were fooled and thought they were actually talking to a real person based on the responses they were getting. Now, this particular claim of passing the Turing test has a lot of skeptics. And the primary reason is that Eugene Guzman is sold as, first of all, a child, a 13-year-old, and second of all, a non-native English speaker, someone from Ukraine. So that puts a little bit of doubt in your head when you see things that might not be accurate answers to your questions. And so some think that the 10 out of 30 humans that were fooled were under the assumption they were talking to a young non-native English speaker. Now, Google Assistant, I think, is a legitimate claim of passing the Turing test. This is a headline from Engadget magazine from 2018. And if you've seen Google Assistant, and I would definitely encourage you to go to YouTube and look up Google Assistant, there's an example video from Google of Google Assistant calling on the phone to make a haircut appointment. Google Assistant talks to the receptionist on the other end. There's a back and forth. The haircut appointment gets scheduled, and the receptionist has no idea they're talking to a computer. So by that measure, the computer is passing the Turing test, and it's very impressive. And the computer even talks like a human and pauses and says, the kinds of things that we do. There's also a funny video online of Google Assistant talking to a non-native English speaker, and that conversation goes off the rails pretty quickly. So it's not perfect, but nonetheless, a very impressive technology. Now, there are two types of AI that people work on. Top-down AI is the idea of building a machine that mimics the human brain. So if you remember the character Data from Star Trek: The Next Generation, Data had what Isaac Asimov, the great science fiction writer, called a positronic brain, an artificial brain that could function, at least in practical purposes, very similar to a human brain. Now, it turns out that creating artificial brains is very challenging because we don't even understand how the human brain works. How are we going to design an artificial brain? What most of us do is bottom-up AI, things like deep learning neural networks, which are composed of simple building blocks. Each node in a neural network is a very simple mathematical function, but together, working together, they exhibit very complex behavior. Now, just as a point of trivia, the phrase AI was coined, or at least solidified, at Dartmouth College at a workshop in 1956. A lot of the leaders in the AI space came together, and at that time, everybody was calling it something different, things like cybernetics. So they came together and said, okay, we need a unifying phrase or word for our discipline, and that's how they came up with AI. Now, AI in medicine has had a very interesting history going back to the 1960s, when computers were really first starting to come online. Things like the Altair 8800, the PDP line of computers. And of course, in 1977, we had the trifecta of home computers that you could go out and purchase and bring home and use, like the Apple II computer, the Commodore PET, and the Radio Shack TRS-80. So during that time, prior to that time, AI was really a science fiction exercise or a philosophical exercise. And when computers came on the scene, we could, for the first time, start to implement AI algorithms and put them to the test. And so during that time, there was a lot of hype and promises about what AI could do, a lot of excitement. And then, of course, as we went through the 1980s and started implementing AI, we discovered that AI wasn't solving hard problems the way we thought it would, and that led to what we've called for many years the AI winter, when AI became a bit of a dirty word. If you worked in the AI space, you didn't want to tell your friends you were working on AI. They would think you were crazy for working on something that didn't work. But something happened in 2010 to change all of that, and I will get to that in a minute. But first, I want to just give a brief overview of a type of AI that was common in the 1970s and into the 1980s. This is an overview of what's called an expert system. So we have a question, in this case, a clinical question. What dose of warfarin, a blood thinner, should we give to a patient maybe coming into the ICU? Maybe they've been in a car accident, et cetera. Now, the first thing a system needs, a computer would need to answer a question like that, is some knowledge. And so that's in AI what we call knowledge engineering. We need the experts, in this case, clinicians, to give the computer knowledge. And often in expert systems, that knowledge is represented as if-then rules. So for example, if the patient is older than 65, then we probably should give them a lower dose of warfarin. So that all goes in a database, a knowledge base, with all the rules. Now, we also need a set of facts about the patient. So clinicians extract the facts, the patient's age, what's the patient's sex, what is their weight, et cetera, what medications are they on. Those facts all go into what's called the memory of the expert system. So these are just the pieces of information about the patient. And then what makes this work is what's called the inference engine, which is basically a set of probability statements that takes the rules, puts them together with the facts, and generates a probabilistic statement about what the answer is. So these were quite common in the 1970s and 80s, and were even implemented. This is Shortlift's Mycin program from the 1970s. Ted Shortlift is one of the founding figures in the discipline of biomedical informatics. And for his PhD work in the early 70s, he developed an expert system for prescribing antibiotics for ICU patients presenting with infection. Mycin works just like what I showed. It has a set of rules. It has a set of facts or patient data that are put together in the explanation system, the inference engine, to answer the question. Now, the exciting thing was that Mycin actually worked. Here's a study that was published in JAMA in 1979, comparing Mycin to a number of experts, including faculty, infectious disease fellows, medical residents, and medical students. And you can see Mycin came out on top. So that was pretty exciting. Unfortunately, short-lived mycin was never used in clinical practice, mostly because of ethical and legal issues. You could imagine your loved one arriving at the ICU. You find out later that they passed away, and you find out that it was a computer that prescribed the wrong medication. You could imagine the lawsuits that would come from that. Further, mycin required up to 30 minutes or more than 30 minutes of physician entry, data entry. Um, and if you search for mycin and short-lived on YouTube, you can find a video of mycin in action, and you can get a sense for how long it takes for it to work. And of course, no physician, no clinician today has that kind of time on their hands. Here's one of Shortlift's books about mycin from 1976. You can still find these on eBay from time to time or other used booksellers. And here's a book on expert systems from 1984 by Buchanan and Shortlift. Okay, so that brings us today. And I mentioned earlier that in around 2010, the AI winter ended. And it was IBM Watson that really ended the AI winter. And Watson was a very, very impressive technology when it came out. And IBM, this was really a tour de force on IBM's part. They put together lots of computer science and informatics technology, things like natural language processing, information retrieval, knowledge representation, machine learning, et cetera. And what impressed everybody with Watson is that it was able to beat the best Jeopardy game show contestants in the world, and do so pretty convincingly. Now, to beat the Jeopardy champion, Watson had 200 million pages of information, taking up about 4 terabytes of disk space. Most of that, interestingly, was taken from Wikipedia and other encyclopedic sources. Watson had 2,800 compute cores, so it had a pretty big supercomputer behind it, as you might expect for IBM. It also had 16 terabytes of RAM, and of course, no internet connection, because the Jeopardy champions don't have access to the internet either. So if you think about it, this was a very impressive feat, because the human players have to see the answer. They have to think about what do they know about the answer. They have to access their memory. They have to formulate a question. They have to assess the probability of which they're right. And then they actually have to buzz in. And all that has to happen in less than 3 seconds. So the fact that a computer could do all of that in less than 3 seconds is quite remarkable. Now, if you're interested in the Watson story, there are a couple pieces I recommend. The first is this piece from AI Magazine in 2010, which is written by the Watson group, and they talk about their development process. Now, this is a pretty long article. It's a bit dry reading, but there's some really interesting nuggets of information in here. One of the things that really struck me is that they were struggling with Watson. Watson wasn't working. And what really turned the corner for them was getting everybody in a room all day. They brought all the scientists into a room. That's where they worked all day long, forcing them to interact with each other. And once they started doing that, Watson really took off, and they started overcoming some of the challenges. Now, IBM, on its building on its success of beating the Jeopardy champions, rolled out Watson for oncology, and they wanted Watson to be used in the healthcare industry, and in this case, specifically to make decisions about what chemotherapy, for example, to give a cancer patient. And there were several health systems and cancer centers that signed up for Watson, including Memorial Sloan Kettering and MD Anderson Cancer Center, and they really put Watson to the test. And at the end of the day, Watson did not perform as well as their oncologists, which was deemed by some to be a failure for Watson. And in fact, MD Anderson pulled out of the Watson project after spending $60 million on it. So this generated some bad headlines. This is my favorite. IBM Watson is the Donald Trump of the AI industry. I think that's pretty harsh. I don't think Watson deserved that. I think Watson is a phenomenal technology. I think the problem that IBM had was they pushed it out into the healthcare industry a little too quickly. I think it needed a little bit more time. But there are some Watson success stories for sure. It is an impressive technology, and I think it has a bright future. But I think IBM made a few missteps in the beginning days of Watson that led to some of the negative headlines. This is a piece from Stat Magazine a couple years ago that gives a nice overview of the Watson project and its history. And this is a more recent one from 2019, how IBM Watson overpromised and under-delivered on AI healthcare. And so this is also a nice review about the project. Okay, so why artificial intelligence? Why am I interested in AI? Well, I'm very interested in how we make decisions about uh, what statistical or computational methods to choose when we're presented with a data analysis challenge. Now, if I was to give a data set to everybody listening and say, let's come back in a week, you can do any analysis you want to. We'll compare notes and see how everybody did. Every person analyzing that data would take a different path through the data set based on their education, their training, and importantly, their experience with data analysis, right? We all gravitate to certain methods that seem to work in our hands for our particular data sets, things that we have experience with, that we like, that are easy to use. And so I'm interested in whether we can get a computer to do that. Can we get a computer to select methods, run analyses, and learn from that experience and improve with experience? So that's the motivation for our PennAI project. So I'm going to quickly step through the different components of PennAI, starting with the machine learning engine. So again, the goal of this project is to get the computer to do the machine learning for you, to make machine learning accessible to everybody, regardless of their background or expertise. So the first thing we needed was a machine learning library, and we adopted the scikit-learn library, which is open source, all coded in Python. It's very comprehensive. It has a large selection of machine learning methods for classification and regression, as well as a number of pre-processing methods. So we adopted that as our machine learning library. The next thing we needed was a controller. We needed a way for the AI to grab a data set, grab a machine learning method, set the parameters, launch that on a computer, get the results back, and do something with it. Now, we started building this ourselves, and I ran across this open source project on GitHub called Future Gadget Lab, which did exactly what we wanted it to do. So we adopted this. And the next thing we needed was a database. We needed a place to put the data because we wanted our AI to have a memory and we wanted it to learn from experience. We adopted the MongoDB database as an open source and free database. Mongo is what's called a document store. And what we do is we represent each experiment, the details of the data, the machine learning method used, the parameter setting used, and all the results as a JSON file that gets dropped into this document store, so that every machine learning analysis performed by the computer or performed by the user is saved, and we have a memory of that. And then we can convert that into knowledge used by our AI engine. Now, the AI engine that we developed is based on the idea of a recommender system. So like I said, we take all the machine learning results, we represent it in a data structure that looks something like this, where every row is a machine learning result. And we have columns with indicator variables for the data set that was analyzed, the machine learning method that was selected, the parameter settings. And we also have what are called meta features. We have more than 50 meta features that we measure on every data set. Things like the sample size, the number of features, the distribution, the correlation structure, et cetera. And we provide that to the algorithm so that it can learn the context with which a particular machine learning algorithm might work. So we have all the meta features in this data file. And then we have a column of performance, like, for example, the area under the ROC curve. So this is the raw material that we then analyze, and we ended up using a singular value decomposition method, which is good for sparse matrices, which I'll say more about in a few minutes. And from that, we build a recommender system. So when you have a new data set, you can feed it in. The algorithm makes a prediction about what machine learning method should be used, and then the AI can launch that automatically on your data. So the next thing we needed was a way to visualize the results and a front end to allow users to intuitively interact with the system. And that was very important to us. This had to be easy. We want this to be accessible to not naive users, people who have never done machine learning before. So when you log into PennAI, this is what you see. Uh, each square on the screen is a different data set. And for each data set, we show the best machine learning method found thus far. We show the testing accuracy estimated from cross-validation. We show the number of machine learning results in the database for this particular data set. Now, all you have to do if you want to do machine learning is load a data set into PennAI as a CSV file. And then once it's loaded, all you have to do is push this AI button. That turns on the AI, and the AI recommender system will take over and, based on its experience, start launching machine learning jobs and filling the database. So it's that easy. You load a CSV file, you push that button, and you're doing machine learning. Now, if you want to do the machine learning yourself, you can push this blue button, and we have a preset number of commonly used machine learning methods, things like random forest and gradient boosting. And when you select a method, you automatically see the parameters for the methods. You can select the parameters, hit launch experiment, and the machine learning job will run. So it's very simple to do a manual machine learning analysis as well. No coding involved, just point and click. When the analysis finishes, this table of results comes up. Every row is a different experiment. You can sort it by accuracy, so you can see the best performing results here at the top. And you can do a couple things from this table. You can click this action button here, where you can download the model, and you can download the Python code that generated the results. So PennAI writes the Python script for you, and you can take that, apply it to other data sets for reproducibility. You could share it with other people online, for example. Now, if you click on one of the rows, we have a nice dashboard that comes up that shows different performance metrics, such as the area under the ROC curve, the accuracy of the classifier. We show the confusion matrix. We show the ROC curve with a 95% confidence interval. We show some details about the analysis in the upper left. And then we also provide a couple tools for interpreting the result, including feature importance scores. So the way this works is we randomize each feature one at a time, repeat the machine learning analysis, and look at the change in accuracy. So the bigger the change, the more impactful the feature is, or the more important the feature is for the overall result. So that gives you some clues about what the important variables or features are in the data set. Now, we just published in July of 2020 a paper in bioinformatics where we do a very thorough evaluation of different recommender systems for PennAI and put it through its paces with a real data set. So I'll just briefly review what we did in this paper. The first thing we did was took 160 publicly available data sets from the Penn machine learning benchmark set and ran PennAI sequentially on these different data sets in different orders to watch how it learns over time. And so the x-axis is experience. So think of this as the number of data sets of experience that PennAI has. So more experience as it moves to the right. And then on the y-axis, we have the change in balanced accuracy between the model that PennAI picked and the model that we know is optimal for that data set from a comprehensive grid search. So the lower the value, the better. And then what we've done here is compared different recommender systems, starting with just a random recommender that randomly, up here in the blue circles, that randomly pick machine learning methods in parameter settings. And so think of that as kind of the baseline performance. The yellow is if we pick them based on the average past performance, so that's not much better than random. And then we have a couple other algorithms in here, some K nearest neighbors algorithms, a clustering algorithm, but the one that performed the best was this bottom purple one, the singular value decomposition that I mentioned earlier. So that's the one that we include in PennAI. Now, one of the questions I often get when I talk about PennAI is, well, how does this compare with other automated machine learning algorithms that are out there? So we compared PennAI to HyperOpt and AutoSclern, which are two of the best AutoML methods. And Teapot, PennAI performs quite well compared to these methods, and actually is in this case on par with autosclern. Now we wanted to apply PennAI to a real data set. And we decided upon this paper, which was published in Scientific Reports in October of 2019. And the authors used the MIMIC data, which is a electronic health record data set with about 60 patients from the ICU that you can apply for and get access to fairly easily. And it's a very rich data set. It has a lot of time series data for things like blood pressure and oxygen levels from the ICU. And so what the authors did was they used a long short-term memory neural network, or a deep learning neural network with a time component, to predict septic shock using different values in this data set. So we use this as a benchmark to compare PennAI to. So the top part of this table shows the PennAI results. So each row is a PennAI result. We have we let a naive user use PennAI and generate a few manual analyses as well that we included in here, just trying to think about how PennAI would be used by a user on a data set like this, kind of simulating a use case. So PennAI found that gradient boosting with these parameters was the best method. It found that automatically without human intervention. Based on 5-fold cross-validation, it had a testing accuracy of about 0.9. And then on a holdout data set, it had a validation accuracy of 0.85. So that was the best result. And that gradient boosting algorithm took about a minute, 2 minutes to run. Now we compared that to a tuned logistic regression model, which had an accuracy on the holdout data of 0.81. And the LSTM deep learning algorithm had a performance of about 0.86, which is about the same as the gradient boosting result, certainly within the confidence interval. Now, interestingly, PennAI ran all of these analyses along with the user in a little bit more than an hour. It took the deep learning algorithm 30 hours to generate this result. And I think this took quite a bit of tuning and experimentation from the authors, whereas PennAI did this automatically. Here's the ROC curve with the 95% confidence interval for the PennAI result, the gradient boosting result. And here are the feature importance scores. And you can see these different ICU measures, things like oxygen, saturation, systolic blood pressure, pH, et cetera. Okay, the PennAI software is open source. It's freely available. It's on our GitHub here, listed here. It is built on several Docker containers. And it's important to note that you install PennAI on your own server behind your own firewall. So no information is transferred. It's all self-contained on your own server. We don't get to see your data or your research results. So you can download it, install it with smaller data sets. It runs just fine on a laptop. I've run it on my laptop before, or desktop computer. So I'll stop there, and let me just acknowledge the PennAI team. Weishan Fu has done a lot of programming on the system. Bill LaCava is a research associate that developed the recommender system and was lead author on the bioinformatics evaluation paper I mentioned. Michael Stauffer has done a lot of work on the front end GUI for PennAI, and Heather Williams is the lead software engineer on the project. And I really sincerely thank her for all her hard work to see this over the finish line. Here's a couple grant sources that helped pay for PennAI. My email address. I'm on Twitter at morejh, and you can get more information about PennAI at pennai.org, or feel free to email me your questions. Thank you very much.